This is part 2 of the series Similarity, and here we have a specific example. We're looking for the value of n, the side length yz. We were given a similarity statement. ABC is similar to xyz, and so we know that AC corresponds to xz, BC corresponds to yz. So let's go ahead and set up our proportion to solve this. Now the way I like to do this is I always like to have, this is personal preference only, but I like to have my variable that I'm looking for on the upper left of my proportion. So I'm going to start with this side first. So let's say that n is to yz. yz corresponds to BC, 6, as we come back to our original triangle, 12. 12 is xz. xz corresponds to AC. AC is 8. And we just multiply both sides by 6. 6 divided by 6 is 1. N equals 12 times 6 divided by 8, which is 9. Just as a verification, we'll go ahead and check our answer. The ratio of 6 to 9 has to equal 8 to 12. So 6 to 9 equals 8 to 12. And so 6 times 12 is 72. 9 times 8, 72. And so yes, this is a true proportion, so 9 is the correct value for n. All right, let's move on to another example. In this example, we're going to have a demonstration of a fundamental principle involved in similarity, and that is the ratio of any corresponding length in similar figures is the same. It doesn't matter whether it's corresponding side lengths, corresponding altitudes like we have here, whether it's perimeter, any measurement, any length measurement in similar figures is going to have the same ratio as the scale factor between those two figures. So we'll treat this just as any other side length, even though it's not a side length. So we can say n, because I like to keep the variable in the upper left, n corresponds to the altitude here, 4, as xy corresponds to AB. So 18 corresponds to 12. Multiply both sides by 4. N equals 18 times 4 divided by 12, 6. Again, let's go ahead and verify that the ratio of corresponding side lengths AB to xy is equal to the ratio of our altitudes. So 12 is to 18 as 4 is to 6. So 12 times 6, 72. 18 times 4, 72. So they equal. So we verified that the ratio of any corresponding length, whether it be altitudes, medians, side lengths, they're all equal to the scale factor. Now in this case, we were dealing with what scale factor? Can you see it? It's 12 divided by 18, which is destination divided by source. So this would be the scale factor. 12 over 18 would be the scale factor between XYZ and ABC. It didn't matter which one we used. We could have taken the reciprocals of these and used the scale factor from ABC to XYZ, which would have been 18 over 12. It just doesn't matter because the ratios are always going to be the same from one to the other. All right, let's move on and look at a different example. Here we're going to further explore the idea that the ratio of any corresponding length in similar figures is equal. So we're going to take a look at just the simple ratios, AB to XY, so that's AB to XY is 12 to 18, which is 2/3, and BC to YZ, 9, so YZ, which is 6 to 9, is 2/3, and AC to XZ, which is 8 to 12, is again 2/3. Now let's take a look at the perimeters, the ratio of the perimeters. Of ABC and XYZ. The perimeter of ABC is 12 plus 6 plus 8, which is 26. And the perimeter of XYZ is 18 plus 9 plus 12, 39. Let's take a look at the ratio. Since we've been using the values from triangle ABC first, we'll put 26 over 39. They have a common factor of 13. 26 divided by 13 is 2. 39 divided by 13 is 3. And you can see that the ratio of the perimeters is equal to the ratio of the corresponding side lengths. So the perimeter of ABC to the perimeter of XYZ is the same as the scale factor between these two triangles. Now again, this is the scale factor. Since AB is in the top, that's our destination, so it's the scale factor from here to here, which means the perimeter of this is 2/3 the perimeter of this. So some basic relationships here that are very, very important. Doesn't matter whether you have altitudes, side lengths, perimeters. The corresponding lengths between these two are in the exact same ratio as their scale factor. So let's move on to a new topic. Now we've looked extensively at the relationship between the ratios of any corresponding lengths, and we learned that the ratio of corresponding lengths in similar figures are all equal. Now we're going to be exploring the relationship between the ratio of the lengths of any length measurement and the ratio of areas between similar figures. And the relationship might not be as surprising as you might think. So let's start off and let's generate the ratio of two linear measures. Since we're going ABC and XYZ, we'll again start with BC here. And I'm going to call this length measurements. So this length measurement, we have a 6 to 9. So BC corresponds to YZ, 6 to 9, which is 2/3. Now, as we've learned, the corresponding side lengths of both of these figures are going to have the exact same ratio. Let's take a look at the area of triangle ABC. So the area of ABC is 1/2 the base, AC is 8, times the height, which is the altitude. So that's going to be 8 divided by 2 is 4 times 4, 16. So that's the area of ABC. The area of XYZ is going to be 12. So 1/2, 12 times 6. 6. So 12 divided by 2 is 6. 6 times 6 is 36. So I'm going to put a symbol here for area. And the area is, let's use ABC first. So that's 16 is to 36, which simplifies to 4/9. So we have this relationship, 2/3 and 4/9. So the ratio of our areas is 4:9. The ratio of our lengths of any length measurement is 2/3. What do I have to do to this ratio to make it equal to this? Well, clearly 4 is 2 squared and 9 is 3 squared. So that's all we have to do is take our length measurements and square them, and only then can we put an equal sign in here to say that these are equal to this. So what that says is that the ratio of the areas is equal to the square of the ratio of the corresponding side lengths. Stated more formally, the areas of similar polygons, the ratio of the areas of similar polygons is equal to the square of the ratio of their corresponding side lengths. Very important idea here. Let's go ahead and put this into practice in an example. In this example, we have two rectangles. Rectangle PQRS is similar to rectangle TUVW. We're looking for the area of this rectangle PQRS. We have the area of this rectangle, and we have corresponding side lengths, PS and TW. So let's begin and see how to find out what the area of PQRS is. Now I'm looking for the area, and I have side lengths. So the way I'm going to set this up is just to keep things nice and organized. I have length measurements, and I have a measurement of 4 and 12, and area measurements. And I have a question mark here and an area here. So I like to put the unknown on top. So I'm looking for the area. We're going to call this area X, just because it's an unknown. And the known area is 42. Now this X corresponds to PQRS, so this number should correspond to PQRS. So that's 4. And this number corresponds to TUVW, so I'm going to use the 12. Now we have no sign here relating these two. Again, how do we relate the ratio of areas to the ratio of side lengths? We just learned that the ratio of the areas is equal to the square of the ratio of the side lengths. So what we have to do is to square this ratio. Now we can set them equal to each other, and we can go ahead and solve. Now it's not necessary to simplify. You can if you want. This simplifies to 1/3. Don't forget to square if you do. One of the reasons I sometimes avoid doing that is to avoid the mistake of not carrying down the squared term here. But we remembered this time, so we're okay. 1 squared is simply 1, and 3 squared is 9, and that equals X over 42. Now we multiply both sides by 42. That goes to 1. Multiply by 42. And we have 42 divided by 9 equals X. And that simplifies to 14/3 equals X, which is approximately equal to 4.66 repeating. So that's an example of how to find areas of similar figures. Again, the key is the ratio of the areas is equal to the square of the ratio of corresponding lengths. And it doesn't matter whether the lengths are side lengths, altitudes, perimeters, it all works. It's all the same on this side. Okay, let's move on to another topic.